little bit. Is anybody this their only class for the day? Then they can. Oh, I'm sorry. I'm sorry.
Just like for the tests, we got right, and so in print presentations, they were like they were just like the experts, like you could make a link that way, and so I think it's
yes,
and so that's how I got into class. I didn't have to do.
But you'll get into that more right now.
And so now with online about central limit theorem.
But yes, you should have. The idea is set the experiment up so you're only controlling one independent variable.
I can use my.
Match across the board.
I don't know if they'll make sense to you,
Oh,
but I can use my central limit theorem now.
Oh, really?
I know. I know you do.
Well, I can make a copy, or you can make a copy for yourself.
That would be really helpful, actually.
That's true. I mean, I get up at 4 because the same reason. It's the same reason. I get up, get my workouts in, ready to go. Of course, I passed out by 8.
Like I said, I don't know if that'll make sense to you.
Well, yeah, for many reasons. But.
She kind of went really fast.
All right, let's get back into this. Now, this is great. Philips Flathead, Mac, Windows, whatever. But the problem is this targets this, but not perfectly. It targets it on. Say that again, nice and loud. It targets it on average. Was that Dylan? Thank you. Whoever said that. I just heard a male voice say it. Give Dylan credit. Oh, wait. This is wait. And this targets this, but only on average, which means if we do a bunch of studies and we collect a bunch of p-hat values and we average those p-hat values together, that average will hit this. Similarly with x-bar, if we get a bunch of x-bars, average those, it hits this. If we only get one x-bar alone, it won't necessarily hit this. So what happens, and you'll see this momentarily, what happens is you get what's called sampling error. Linda, this goes back to something you said about 15 minutes ago, about standard deviation. So, if you will, I'm going to show you a spreadsheet here in a minute that actually makes this a little more dynamic. We'll get to that. So, here is the population. This is just, don't draw this, because it's too annoying. Just check it out and see if you can see what I'm getting at with numbers. Here's a parameter you're trying to estimate. Let's say it's about at that's about 0.49, maybe 0.48. That's the population percentage of something that you're measuring, whether it's pain reduction, whether it's President Obama's approval rating right now, whatever it is. It's out there somewhere. You don't know what it is. Okay? Here are individual samples that you draw around that population, or from that population. So Alan, like you said before, you don't get that. You're never going to know what that is, right? What you're going to get is, you're going to get a sample, most likely one sample. If it gets replicated, which it should, if it gets replicated, you're going to get lots of samples. And if you get lots of those samples, and you average all those sample values together, you get this. And guess what that is? It matches the parameter you're estimating. That's the beauty of it. On average, it matches. If you want a mathematical proof, which it sounds like maybe one or two of you do, I beg you, go check out the proof online. It's really, really slick. I had a lot of fun doing it. But if you just trust me, and you can trust me because I wouldn't lie to you. If you trust me, if you can replicate a study enough times, you will get that average. But here's the problem. How many resources does it take to replicate a study enough times? Unfortunately, it generally takes infinite resources. Damn it. We don't have infinite resources. For example, suppose you're trying to test the shear strength of bolts in an engine housing in a Honda CR-V 2012 limited edition. The only way to do it is to keep running until the engine falls off. Well, you're going to run out of Honda CR-Vs after a while, right? You're going to run out of them. You can't just continually keep bringing them in, running them until they explode, and then getting another one in. So what you usually get sometimes is one sample or a couple samples. So you might only get one sample. You might only get one sample like this. So then what you have to do is, this does not match the parameter. Sometimes it's very far away. Did you catch all the samples on the previous slide? Some of those guys are way, way far away. These guys are way underestimated. These guys are way overestimated. Yes, yes. So what if you get one of those that's like out there? Now again, as Alan said, we're not going to know what that is. So we have no idea that that's quote unquote off, right? So how do we make our estimate better? By applying a measure of standard deviation around it. How often when you read the polls in the news, go ahead, Katie!
So I'm just trying to like relate this
Go!
things in
Yes,
my
please
head.
do.
I don't know if that makes sense.
You're making me happy right now.
Okay. So my dad has this like carbon fiber anyways, a bike fork.
Good!
And he has this machine that like hits on it to see how long it takes
To
for it
break.
to break. So would that be just one sample? It's kind of infinite because it keeps going.
Because, yes, and rock climbing equipment does the exact same thing. Any rock climbers in here? Kate, you are. I know you are. You got a couple. They'll test cams. What camming is a protective unit you put in like a crack in a rock. You put that in there, you clip your rope to that, so if you fall, it's supposed to catch. In that terrible movie, Vertical Limit, it's the things that were pinging out in that first scene. Ping, ping, ping. They don't do that if you place them right. And they don't do them if they're built right. So what you do is they test each of those to what they call 2/3 of their failure capacity, much like your dad is testing to destruction. What he'll do is he'll test one fork to destruction, a second fork to destruction, a third fork to destruction, for example, and as many as he can afford to test, and then average those results. The average of those results will be that number right there. But then, each of the forks is going to react a little bit differently, isn't it? Some of the forks are going to fail after a couple hits. Some of the forks are going to fail after a lot of hits. Which means there is not just an average in that sample, there's also a standard deviation in that sample. And that's what this is. It's a measure of uncertainty. Saying, okay, the center of my sample is here, but it could be as low as this, or it might be as high as this. Now, obviously, you want to make that as narrow as you can. You want to make that as narrow as you can, because you don't want to say something like, I am between 0 and 100% sure that fork is going to fail after 200 hits. Because that's useless, right? I mean, it's true, it's also true. But it's useless and true, yes? It doesn't give us enough precision. So we get accuracy but no precision. With precision, you have to draw more and more samples. And that's the importance of replicating studies. If you can keep replicating a study and getting similar results, the precision gets better. Thank you for that corollary. Hang on one second, Blake, I got you in a second. Entrepreneur is a company in town. They make rock climbing holds and walls and things. About 10 years ago, they were trying to go to a more eco-friendly rosin to make their holds. And they wanted to make sure it was as strong as the other rosin, which is terrible. If you ever watch people make rock climbing holds, they're wearing like hazmat equipment to make it because it's really, really toxic crap when it's in liquid form. I guess once it dries up, it's totally fine, I guess. I don't understand chemistry. I didn't climb it for a while. Nothing's wrong with me, right? Watch it. So I did a test for them. I did a stress test for them to see, and a test of failure. Basically put a kilonewton measure on a weight and then pull down until it cracks, and then keep pulling until it breaks. And what I was able to see was, they actually crack much earlier than the old rosin, but once they're cracked, they actually last longer. But Entrepreneur said, you know what, that's great and all, but I can't have a bunch of holds cracking all over rock gyms and say, it's fine, keep climbing on them, obviously. So it's just like your dad and his forks. It would be one thing like, hit, crack, oh, it's cracked, keep hitting it, hit, 3 days later you're still hitting and holding. You're going to have a hard time selling the Tour de France teams on the fact that it's cracked, it's totally fine. That's what Rule does on his bike, not what a professional does. So similar, very nice connection. Thank you. Blake, go.
So in this kind of made up example, right? These are probably percentages, say.
Exactly.
Is there any benefit to going over 1? Like if your standard deviation is at 140?
Mathematically, it's going to have to go over 1. Blake just has a very, very good practical versus theoretical connection. This is going to happen a lot in this class. Because there's math behind everything we're talking about. But sometimes, because of the math doesn't understand the application. There is no benefit of going over 1 in certain applications, if that is just a percentage. Now suppose that were what's called a relative risk. So suppose a drug is concerned that it might be treating, say, high cholesterol, but it might increase the risk, say, of platelet clumping, or increase the, thank you, liver failure, thank you, something similar, liver failure. You could go over 100% with that, because you might be like 3 times as likely to develop liver failure on the drug. That'd be 300%. So percentages can go over 100%, just not the population percentage you're used to talking about. Because probabilities top out at 1. But rates of risk don't. They can go as high or as low as we need. You can have a negative rate of risk. You're less likely to get it than the other. You can have a greater than 100 rate of risk. So yes and no, depending on the context. We'll attack all the contexts in here. Great question. Great question. Other ones before we go on. Because I love what Blake said. because we have made up data. Well, the hell! Let's make some of our own data that's not made up. I like that idea. I like that idea. Hell with this. Let's turn this off. Let's do something else. So here's what I want you to do.